Test, 1, 2, 3, 4. All right. Hello and welcome to today's solution session. So today we once again had a team contest with 10 problems. Most of the problems were from a sub-regional contest in the northeastern region, which is Russia. And they were of corresponding difficulty, as you could see. So let's now walk through the problems in order of difficulty and let's see what to do with them. So the easiest problem today was probably the problem homo-hetero, where we had to find out two things about the sequence at each time, whether it contains at least one duplicate item and whether it contains at least two distinct items. So there are plenty of data structures that could be used in these tasks. Probably the easiest way to implement this is to use a map where for each item we store the number of times it occurs. So whenever a new item appears, we take a look into the map and we increment the counter. Whenever an item disappears, we take a look into the map, we decrement the counter, and we erase the entire record if the counter reaches 0. So at any moment, the size of the map is the number of distinct items. And the other thing we need is a counter, a plain simple count of all items. So in order to see whether there are two distinct items somewhere in the sequence, we check whether the size of the map is larger than 1. In order to see whether there are duplicates in the sequence, we can compare the count of items, which we simply increase, decrease, and the size of the map. So if the size of the map is strictly smaller than the count, then some of the items has to be there twice or multiple times. So this was probably the easiest way to implement it, but there are plenty of others. You could have a map and a set or something similar. All right. Any questions here? Everything clear? I believe almost all of the teams had this task correct, so I would be surprised if there were any questions. A second easy problem for today was the longest common subsequence problem. In this case, we are given two long sequences. And we are guaranteed that one of the sequences doesn't contain duplicates. It contains n unique items. So the first step of the solution is to identify which of the sequences is which. This is very easy. If you have them stored, for example, in vectors, just initialize a set with this vector and compare the sizes. So if the size of the vector and the set is the same, then this is the sequence where there are no duplicates. So let's switch them up. So this is the one with unique items. And in this sequence, there can be some repeats. Now, if we want to find the longest common subsequence of these two sequences, what we need to do is to pair the numbers in some sense like this. And these pairs must go in the same order on the top and on the bottom. What we do know is that each of these items that are in the first sequence can occur in multiple places here, and we have to pick the right occurrence. So the trick here, what we can do, is we can relabel the items. So we can number this sequence 0, 1, 2, 3, 4, 5, 6, and so on. And for the second sequence, for each item, we can check whether it is contained in the first sequence. If it is not, we can simply throw it away. And if it is in the original sequence, we will find it's the place where it's there. So to do this, we can have a map which will map the value that occurs in the first sequence to its index. So for each value, we can then find in logarithmic time whether it is contained in the first sequence, and if yes, what is its index. So each time we take a look here, we find this key in the map. If it's not present, then we can throw this item away. If it is present, then we replace it by the index. So if this value would be stored here, then here we would get a 1. Here we would get an x again. Here we would get a 4, a 6. If this is, again, this item, we would get a 1 again, and so on. And now what we are looking for after this translation, in this sequence, we are looking for the longest increasing sequence. So we have to pick a subset of these items that occurs in the original order here. And the original order are simply increasing indices. So in this way, this longest common subsequence problem can be turned into a longest increasing subsequence problem. And to find this longest increasing subsequence, there is this standard algorithm in O and log n time. Actually, this can be done in two different ways. Either you can use an interval tree because you know that the values are small, they are only from 1 to n. Or you can use the standard algorithm that works always, which is that for each length, we are computing the smallest element at the end of an increasing sequence of this length. So at the beginning, there are no increasing sequences. Everything is infinite. And we are processing the items one at a time. So right now, we would get a 2. And this would mean that we can construct an increasing sequence of length 1 that ends in a 2. We would now get a 1. This doesn't allow us to construct a longer increasing sequence, but we can improve this place. We can now have an increasing sequence of length 1 that ends in a 1. Now we get a 4, and this allows us to construct a sequence of length 2 that ends in a 4 because we can append the 4 after the 1, and so on. And in each step, each time we read a new number from the input, only one cell in this table changes because, for example, right now, if you read something less than 1, you will improve this cell. If you read something between 1 and the 4, you will improve this cell. If you read something larger than 4, then you will improve this one. And it's always only one cell, and you can use binary search to find the correct place. So this is the n log n algorithm to find the longest increasing subsequence, and in this way we can solve the task. All right. Any questions here? Great. So after a pretty much standard task that was using a very well-known trick, now for the task auxiliary. And in this task looks scary at the first glance. What we are given is some incorrect expression, like this one. And we have to fix it. We have to produce a syntactically correct expression only by inserting new characters into this one. And this does look scary until you realize that you have complete freedom in choosing this expression. And choosing an expression in the correct form will help you very much to implement this solution very easily. What you can do, you can always try to construct, for example, expressions of this form. Yeah, so this will be the form we are constructing. And if you can see what will happen now, I can divide it into parts like this. Each part contains 4 characters, except for the terminal one with 3 characters, which is added after the last plus to make it valid. So in each of these parts, I have exactly 4 characters. So if I start with a sequence of length 1000, then I can spend one entire part per each character of the input. And this is exactly what will happen. So if I see a left parenthesis here, then this will be this one. This was a right one. A left parenthesis will become the left parenthesis. If I have a 0 here, then I will place a 0 here. And I'm done. For the plus, I will then take the plus for the left parenthesis, I will take the left parenthesis, and one more. I need a 4, so there will be one more 4, and the end. So in this way, if I start with a sequence of length 1000, I will end with a sequence of length at most 4003. It is clearly syntactically correct. It clearly contains each of the characters. So this was one of the simplest ways. Once again, this was an ad hoc task, so you could do something slightly different, but the main point of this task is don't go into trying to match the parentheses and to create a balanced parentheses expression. There are simple tricks how to do this. All right. Questions, comments? All right. Circles on the screen will be the next task. In this case, we are given a bitmap, and the bitmap is fairly small. The dimensions are just 20,000 by 20,000. And on this bitmap, we have a set of circles like this. And the number of circles is also very small, 100. So this makes our life a little bit easier and more convenient. What we can do, what the task is to find all cells that are white if the circles are painted on the bitmap, so all cells that are contain their centers within the circle. What we can do, as the number of rows is very small, we can process the image one row at a time. This will make our lives very much easier than trying to actually parse the circles and process the intersections. So we will just focus on a single row at a time. And if we now focus at a single row, what we can do, we can process all of the n circles. And for each of the circles, we can check whether it intersects this row. And if it does, then clearly the intersection is an interval of pixels. So for each circle, we compute this interval, and we can then sort those intervals and process them in n log n time. So this solving a single row boils down to the task that I'm given several intervals on a line, and I have to find the length of their union. And to do so, it is enough to sort the endpoints and then to process them from the left to the right. And each time I'm keeping count of the number of open intervals, and so that I know when I'm moving right whether to count this part or not. So each of the rows can be processed in n times log n time. And so the overall time complexity is this, and this is like 20,000 times 100, which is 1,000,000, times the logarithm of 1,000,000, which is something of 100, which is below 8. So this is on order of millions and should be fast enough by a wide margin. Right. Questions? No. So now for example, for the brackets task. What we are given is a bracket sequence consisting of left and right brackets, maybe like this one. And what we are supposed to do, we are supposed to count all of the subsequences that are correct bracket sequences. The trick is that each of these sequences has to be only counted once. So for example, the sequence left, right occurs here, it occurs here, it occurs here, and in many other places, but we only have to count it once. So this is what makes the problem hard. If we were to count each occurrence separately, it would be a much easier problem. In this case, if we are given such a constraint, the task is usually still solvable. What we have to do for each such object that occurs there, we have to pick one canonical occurrence, the one which we will count. So what we can do is for each sequence of brackets that occurs somewhere in the string, for example, for this one, what we will do, we will pick its lexicographically first occurrence. So this one will be this bracket. Now we need two right brackets, so it will be this one, this one, this one, and this one here. So for each such sequence, we can greedily pick the right occurrence we will be counting. And right now, you can imagine a recursive algorithm that would generate all of these canonical subsequences only. What we will be doing is, as we have this sequence of brackets, we are going left to right, and we are at each step, at each character, we are taking a decision whether to take it into the current sequence or not. So imagine now that I picked this one, I picked this one, I discarded this, or I picked this one, I discarded this, I picked this one, and right now, what can I do? I have only two choices what to pick next in order to stay canonical, in order to only pick the leftmost occurrence of each of the sequences. I can pick this bracket, so the next opening bracket, or I can pick this one, the next closing bracket in sequence. I cannot pick anything else because by skipping this one and picking this, I would get a subsequence that is not canonical, that is not as leftmost as possible. So if I would write a recursive program, then in each step tries two possibilities, either pick the next opening bracket or pick the next closing bracket. And this program would also keep track of the number of currently open brackets in order to not to overflow. And this program would generate each of the outputs exactly once. So it would correctly compute the answer. The problem is its time complexity is still exponential because, for example, if you take an input like this, then it is very easy to see that for such an input, if you continue the pattern, the actual number of such subsequences will grow exponentially in the input size. Because in each of these parts, we can, for example, pick one or two pairs of nested parentheses. So each subsequence of the, for example, like this one, here will be two, here there will be one, two again, and so on. Each subsequence is valid, each of them has to be counted, and their count grows exponentially. So the lesson here is that this exponential solution we just found is perfect because what we have to do is we have to turn it into a polynomial one using some memoization. And at the same time, we know that we need to use large integers in order to represent the result because the result can be really large. If the sequence has for 400 parentheses here, then we have 100 such pairs, and this means at least the answer is at least 2 to 100. So we take the recursive solution, we add the memoization, because the current state can easily be represented by two things. The thing is the last bracket we picked and the number of brackets we have currently open at this moment. So in this case, the state would be that this is the last picked bracket and the number of open brackets is 0. So here we can only pick the next opening bracket. In this state, we can either pick this bracket and go to the state this and 2 open brackets, or we can pick this one and go to the state this place and 0 open brackets. And based on this state, we can add memoization and at each moment compute the number of ways in which the rest can be completed into a valid sequence. So this was a very hard dynamic programming task. Questions, comments about this one? All right. Enigmatic device will have to wait for a while. Image grip key. P, rice, and matchmaker. All right. So rice will be the next problem to tackle. So in this case, in this task, we are given a prime P, and we are constructing the following sequence. We pick some value less than P, and we are constructing the sequence 1, A squared, was it A cubed, and so on. And this sequence is computed modulo P, and it terminates as soon as the value repeats for the first time. Well, the first thing to note here is that the value that will repeat for the first time has to be the value 1. This is because this sequence is actually reversible. As we are computing modulo a prime, we can take an element of the sequence and compute the previous element by dividing, well, multiplying by an inverse element. So if we imagine the sequence going like this, you get a sequence in which you always can determine the next value, and you can always determine the previous value uniquely. So it is impossible for such a sequence to start being periodic with a pre-period. This is impossible because for this value we would have two different predecessors, and this cannot happen. So actually what happens is that the value to repeat has to be the first value of the sequence, the 1. So we will, when we pick the A, this will pick some of the values from the set 1, 2, and so on, up to P minus 1, and then it will return back to the 1. So the optimal solution, should it exist, would pick each of these values exactly once before returning to a 1. And now comes a little bit of algebra. If we take this set and the operation of modulo, of multiplying modulo P, this is a multiplicative group, and it is a well-known fact that whenever P is a prime, this group is cyclic, and it has a generator. So there is always such a value A that its powers will cover all possible values. Now, finding a generator is a hard problem. So in this case, if we don't know how to find such a value, we can always ask an easier question: how to check whether something is a generator. This is a very usual design pattern for algorithms because, for example, in many cases, if you can check whether something is a solution, you can use binary search to find the best solution in case the answer is behaving monotonously. If anything better than x is also a solution, if x is a solution, then you can just search for the threshold where still a solution exists. In this case, we will not be able to use binary search because generators behave pretty much randomly. But it is very easy to verify whether something is a generator. So what we now need to recall from algebra is the order of an element. So given an A, its order is the smallest k such that A to the k is equal to 1 modulo our prime P. So we are looking for an element of order P minus 1, such that only its P minus first power is equal to 1 and never before. And we know that for each element of a group, its order always divides the size of the group. So in our case, for each A, the order of A divides P minus 1. So in order to check whether an A is a generator, what we need to do is we need to check whether its order is P minus 1 or whether it is a proper divisor of P minus 1. If it's some proper divisor, then this number is not a generator. So, and the trick here is that we don't have to check all the divisors of P minus 1. If we have, for example, P minus 1 equal to 2 to the 7 times 3 to the 5 times 47, then only all the divisors we need to check are 2 to the 7 times 3 to the 5, 2 to the 7 times 3 to the 4 times 47, and 2 to the 6 times 3 to the 5 times 47. So if we have a value a, what we will do, we will compute the values a to this power, a to this power, and a to this power. And this is a sufficient check for a generator, because if one of these values comes up equal to 1, then we know that a is not a generator. And on the other hand, if a is not a generator, then its power divides p minus 1, and it has to divide one of these values or be equal to exactly one of these values. So what we did is, for each prime, we tried removing it, and this gave us the set of almost maximal divisors. So this gives us a nice simple test whether something is a generator. So take the prime p, which was given in the input, compute p minus 1, find the factorization, and find these almost maximal factors, and then use modular exponentation to check whether a will give the result 1 or not. So right now we can easily check whether something is a generator, and it isn't known whether these generators behave in some nice pattern, and there is no known algorithm that would find them efficiently in a deterministic way. In this case, the inputs were pretty small in order to allow you to factorize easily, so a sequential search was enough, I think. You could try checking whether 2 is a generator, 3, 5, 4, 5, and so on, until you find one, and this was sufficient. But in general, there is no provable deterministic algorithm that will always easily find the generator. On the other hand, it can be proved that the number of generators is fairly large, and you need just a constant number of random attempts in order to find one. So the official solution simply uses a random search. In each step, we pick a random value from this set, and we check whether it is a generator. And as soon as we find one, we output it and terminate. All right, so this is a bit of knowledge that is can be fairly useful if you get a math-biased problem setter. That to find the generator, you just have to do such a check, and that you can do it randomly. And well, to move to a higher level of tricks, then randomization is a very useful trick that can sometimes be used to solve a problem using a shorter code. All right, any questions about this problem? No. All right, so now for a text processing problem, matchmaker. So what we are given in this problem is a pattern matching problem. We are given a pattern, for example, of the form 0, 1, a star, a 4, a 7, a sharp, and a 2. And then we are given several strings, and we have to match these strings against this pattern. In this case, the meaning of the star is it represents a sequence of digits of even length, and the sharp represents a sequence of odd length. So when we now get a sequence of digits, and we have to map it to this pattern, what we will do, first of all, we have to handle the beginning and the end. Here, these have to occur exactly at the beginning and exactly at the end of the sequence. So if the pattern ends or starts with digits, we have to check whether they exactly match. In this case, we get rid of the beginning and of the end of the sequence, and what we have is the rest of the pattern, which starts and ends with a wildcard. We can also check the parity, whether the parity of this matches the parity of the rest of the string. So right now, what we will be doing is we can take the pattern and we can break it into parts, and the parts will be alternately containing wildcards and containing digits. So during pre-processing, when we read the pattern, we will break it into several parts. So, for example, we would have a star, star, star. Then we would have a 47410. Then we would have a hash, star, a hash. And once again, we would have some digits, and so on. And now we have to find out whether a given sequence of digits matches this. So what we'll be doing is we will be matching these parts greedily. We will be looking for the leftmost valid occurrence. And then for each of the sequence of wildcards, we just know the minimum number of things we have to skip at this moment, and also the parity at which we are looking for. So one of the catches in this problem, and the reason why we may be getting a lot of wrong answers, is not realizing that for the hash sign, the count of these signs actually matters, because if each hash sign tells you to skip an odd number of points, then you cannot just concatenate two hash signs and say, I'll skip an even number of digits, because here you have to skip at least one digit, and here you have to skip at least one digit. So this sequence, for example, tells you to skip an even number of digits, because odd plus even is even, but at least two. So what we are doing is we are going left to right. Each time we encounter a sequence of wildcards, we skip the minimum number of required digits. So if we would have, for example, two sharp signs here, we would skip the first two digits. We know that these have to be contained in matching these wildcards. And from this point on, we are looking for this pattern. So we can use either Knuth-Morris spread or Rabin-Karp or any other efficient string matching algorithm to find an occurrence of this string in this one. And we only take this occurrence if it matches the parity. So it has to terminate at the right parity in order for us to take it. And once we take it, we can then continue with the next wildcards. Once again, we skip some characters if necessary, and we look for another substring and so on. So in this way, we can greedily match the contents of the pattern. All right. Any questions here? Oh, all clear. Hopefully. Now, for the horrendous task about the Kripke model. This task is actually quite easy to implement, and the hardest part of this task is not to get scared by the problem statement and to actually force yourself to read through it. So those of you who managed to read through the problem statement and understand it properly were rewarded by having a reasonably simple task to solve. So what we are given is a string of the following form. Where these capital letters are operators described in the problem statement, and the x and the y are variables that correspond to some vertex properties. So what we are given is a graph, and let's parse these things one at a time. So first of all, we will focus on this inner part. GY, what does this mean? We have a graph, a directed graph that looks like, for example, like this. And some of the vertices in this graph have the Y property. So this can have the Y property, this one, and this one. And GY means that for a path, all the vertices on this path have the Y property. And A is a quantifier for all, saying that The property AGY is a vertex property, and the vertices that have this property are the vertices where all paths starting at this vertex contain only vertices with the Y property. So what does this tell us about the graph? If we take the graph and we find its strongly connected components and contract them, so we get an acyclic graph. Which vertices are the good ones? For each of the components, we can say whether it is all Y or not. If a component only contains vertices that have the Y property, then it is an all Y component. If not, then it is not. So, for example, these components can only contain vertices that have the property, and in this component, some of the vertices have the property, but some of them don't. And now we can label all the good vertices where this property holds, which is, in this case, this component and this component. In order for this property to hold, you have to be able to reach only vertices with a Y property. So this means that your entire strongly connected component must only contain such vertices, and also all the components that are reachable from your component must only contain such vertices. So we can find all the vertices where this property holds simply by constructing this. So we find the strongly connected components, we label the good ones, and we then process the graph bottom up to find the vertices. So right now we have a set of vertices where this property holds. And this new property, the outside one, is saying what? These are the vertices where there exists a path through vertices that have the X property into some vertex that has this inner property. So we already have this set of vertices, and we are looking for all other vertices such that there is a possibly zero-length path through X vertices into one of these. So what we will do, we will start a breadth-first search, for example, in this set of vertices, and we will go against the direction of edges, and we can only visit vertices that are labeled by X. And these vertices will also belong to this outer set. So in this way, we can parse this property that these are all vertices such that through vertices with label X, I can reach a vertex where I cannot leave the property Y. So if solving this in a contest, you will probably want to have the strongly connected components algorithm pre-written, and then to take it as a component into a solution and add this additional search at the end. All right. Does this make any sense? Well, so we are left with the last two tasks, if I'm not mistaken. And task number 9 today is image recognition. So what we are given is a set of bitmaps of images, and we have to program a robot in order to walk on the bitmap and to check some cells and to distinguish between those possible images. So this is not such a hard problem. What we need to realize that this is actually a state space search problem. So what is this state space? If we take a look at the robot during some moment in the execution of his algorithm, what is its state? The state are the coordinates at which it is currently standing, and the set of possible images which still correspond to what he has seen so far. Of course, we can encode this set into bits of a number, And as there are at most 10 images, so we get 10 possibilities for the x-coordinate, 10 possibilities for the y-coordinate, and 2 to the 10 possibilities for the set of images that so far corresponds to the measurements at this moment in the program. So this state space is pretty small. It is like 100,000 of states. And what we have to do is we have to examine this entire state space in order to find the best strategy. How does the best strategy look like? I'm in some state, and I have some set of images I still need to distinguish between. So what I will do, I will pick a cell where at least 2 of these images differ. I will go to the cell, and I will make the measurement. And out of these possibilities, we will try all of them, and we will pick the one that will give us the shortest solution. Because as soon as I make the new measurement, my search space splits into from the original state into 2 new states. The new state will be the new coordinates and the set of images, and the subset of this set of images that have white in this cell, and the others will be the subset which have black in this cell when I did the measurement. So this basically gives us a graph of states, and we can use the Dijkstra's algorithm in order to find the shortest solution. All right. Questions, comments? Yes?
What would be the time complexity of such algorithm?
Well, we have 100,000 states here, and most of these states actually will not be reachable because you will only be trying those states where you get new information each time. But even the worst case estimate can be made like this. So this is 100,000 of states. In each state there are at most 100 possible moves because we just have to pick the next cell where we go to. So this gives you like 10 million of edges in the graph. And for the Dijkstra's algorithm, you have to multiply it by the logarithm, for example, of this number. So it's still on the order of millions and should be acceptable. All right. So, and the most nasty task of this problem set is the enigmatic device. No, this task involved a pretty non-trivial operation that was done on the cells of the array. So we had an array, and with each cell independently, we were doing some strange operation. The operation was take the value stored currently in the cell and change it into x squared modulo 2010. And this was done repeatedly and independently for each cell. So what we can do, of course, we can generate this sequence independently for each of the cells. And we know also that the sequence will sooner or later start to repeat. But if the sequences will behave very differently and very wildly, this doesn't really help us. So the first step towards finding the correct solution is to get a feel of how this operation works. Obviously, we just have to think about 2010 different inputs for this operation, because as we are computing modulo 2010, any starting value will, after the first step, lead to one of these and so on. So what you can do is you can actually write a program that will try all possible inputs from 0 to 2009, and for each of them, try to generate this sequence and to find out when does it become periodic. What we will find out is that these sequences actually become periodic very quickly, and the worst case that can happen is for a period of length 2 and period of length 12. And all of the periods for all possible inputs divide the value 12. So what will be happening is that at each cell of the array, maybe after the initial 2 times it is changed, the value will be changing periodically, and the period is very small. So the sample solution uses this fact as follows. What we will do is we will build an interval tree on top of this entire array. So we will have new vertices like this. And we will use this interval tree in order to simulate each of these operations in logarithmic time. What we will need in each of the vertices will be basically the current sum that is that you get when the types of queries we will have to process will be of 2 kinds, as given in the problem statement. So we can either be given an interval, and we will be asked to change each of these values to the next one, or we can be given an interval, and we can be asked for the sum of the values that are currently in this interval. So in order to be able to answer these sum queries efficiently, we will be caching the sums along the interval tree. So each moment when we get a sum query, we just break the interval into the logarithmic number of parts, find the corresponding vertices, and sum these values. And in order to be able to update these values efficiently, what we will be doing is in each vertex we will actually store not only the current sum that currently corresponds to this piece of array, but we will also store the next 13 sums that would be obtained if the entire part of the array was modified once, twice, three, up to 13 times. So we will store such a sequence of 14 values in each of the nodes. And we also need to store the number of times this node was modified in this entirety. This is because if there comes later a change that just hits a part of this interval, for example, in this case, we get a change of only this subpart which belongs to this vertex. But here we have some meaningful information. What we have to do at this moment is lazy propagation. So when this vertex needs to be broken, then we will take the number of changes that was done here, and we will change them here, we will change them here, and we will proceed deeper in the tree. So in this way, we have some vertices that have actual information, and at each moment when we need to, we do the lazy propagation and move this information deeper into the tree. It's probably best, before you start implementing this, to actually try simulating this on paper and to find out what are the exact values you need to store in the nodes and how to do it. All right. So any questions about this one? No. So then this concludes the session for today, and see you tomorrow.